Okay, I want to work an example problem for you. It's problem number 137E. It's on page 31 of your text. I'll read it to you first. A gas is contained in a vertical, frictionless piston cylinder device. The piston has a mass of 8 pounds and a cross-sectional area of 5 square inches. A compressed spring above the piston exerts a force of 18-pound force on the piston. If the atmospheric pressure is 14.6 psia, determine the pressure inside the cylinder. Well, in a problem like this, it's always beneficial to sketch a picture. Even if there's already a picture given, sketching a picture will help get your brain in gear. So I've sketched a picture of the device. Here's our cylinder, here's the piston, here's the spring applying force on the top of the piston from the beginning. In fact, the spring applies a force initially, F sub S force from the spring, of 18 pounds force. The gas inside of the piston has some pressure P. That's what we wish to find. The cross-sectional area of the piston, in other words, if you were to look at the piston in this direction, what you would see is a circular area, and it would have an area of 5 square inches. So we'd like to find out what is the pressure in the gas. Now, if you think about it, the piston applies force to the gas. As we read, there's a mass of the piston equal to 8 pounds mass. So does it apply 8 pounds mass of force to it? No, pounds mass is not force. Does it apply 8-pound force of force to the gas? Yes, it does. Okay, so anyway, we want to know how much pressure in total is applied to the gas. And so far I've mentioned two things that cause pressure in the gas. One of them is the piston, the other is the spring. Is there anything else? Think about it for a minute. Even if you need to pause the video, think for a minute. Is there anything else that could cause pressure in that gas? Okay, so if you've thought about it, the other item that can apply pressure to the gas is atmospheric pressure. The local atmospheric pressure, PATM, was given as 14.6 psia. So if you wanted to calculate the pressure in the gas with just this information, without the atmospheric pressure information, the only thing you can come up with is the gauge pressure, not the total pressure. But I assume they want us to find the total pressure. A lot of times in thermodynamics, you're using total pressure, not gauge pressure. And things like the ideal gas law and looking at properties, you need total pressures. So anyway, the pressure of the gas would be equal to the force from the spring plus the force from the mass of the piston divided by the area of this piston. Because look, pressure is force over area. So what I'm doing is I'm taking the two pressures from the spring and from the mass of the piston, dividing them by the cross-sectional area of the piston to get the contribution per square inch, essentially, of pressure. So then we have to add the atmospheric pressure on top of this, and here's our equation for computing the total pressure in the gas. Now, the force from the piston, we don't know the force from the piston yet. What we're given is the mass of the piston, but force is mass times acceleration. So if we know the mass of the piston multiplied by the acceleration, what acceleration? Well, the acceleration of gravity. So essentially, the weight is the only force acting on the piston, aside from the gas acting up, but we're interested in the force applied to the gas, so that's just the weight of the piston. Anyway, so the mass is 8 pounds mass. The acceleration of gravity, pardon me, is 32.2 feet per second squared. And if you multiply this out on your calculator, you would have force in the units of pounds mass feet per second squared. However, those aren't the units of force we're used to using. What we're used to using is pounds force. So we need to multiply this by G sub C. Now you guys know I don't like G sub C. I just like the conversion factor that takes me from pounds force to pounds mass feet per second squared. Okay, because both of those are force units. Pounds force and pounds mass feet per second squared are both force units. We just use one more common than the other. So anyway, I need to multiply by 1 pound force per, and this is the way I remember it. Whatever memory trick you want to use is fine, but I remember it like this. 1 pound force, 1 pound mass, 32.2 feet per second squared. Why do I do it this way? Well, it's just a memory trick. I know that 1 pound mass will weigh 1 pound force on Earth. In fact, I already know that this weight, or this force, is going to come out to 8 pounds force, but I'm just proving it. And then I can remember the acceleration of gravity is 32.2 feet per second squared, so I just throw it in, and I'm done. I've got my conversion factor. And I can flip this fraction any way I need in order to convert to or from pounds force. So, sorry I had to break the line, but pounds mass will go away, feet per second squared will go away, and numerically, the 32.2 will go away. And that's why 8 pounds mass will weigh 1 pound force when the acceleration of gravity is 32.2 feet per second squared. So obviously, I mean, this was trivial, but I went through this for the sake of helping you understand G sub C. A lot of students are very confused about it. So 8 pounds force is the amount of force that the piston applies to the gas. So now we can plug in numbers into our equation. The force from the spring we know is 18 pounds force. The force from the piston is 8 pounds force. The cross-sectional area of the piston is 5 square inches, and the atmospheric pressure is 14.6 PSIA. Now, PSIA is pounds force per square inch. Now, I've already got pounds force per square inch here, so the units are consistent. That allows me to just plug the numbers in my calculator and come up with 19.8 PSIA. So there's the pressure on the gas. Now, that pressure is due to the atmosphere. It's due to the piston, or the weight that the piston has, or the weight of the piston that has to be supported by the gas, and the force that's being applied by the spring. The one that students almost always forget is the pressure from the atmosphere. It's important in thermodynamics that you remember you have to deal with the pressure of the atmosphere because you need total pressures, not relative pressures or gauge pressures.